Set yourselves up for an endless fiasco of outstanding extent. Balu, the red Goliath star adjusted on the edge of our framework, is passing on dreary messages through the universe. Using the James Webb Space Telescope, cosmologists have uncovered something altogether disturbing about this tremendous, sublime body. As prominent astrophysicist Brian Cox gives a grave admission, the question looms: are we on the verge of witnessing a terrible, infinite blast that could forever change the night sky? To the extent that we may be concerned, we ought to dive into the astonishing, woven fine art of the universe where stars are imagined, live, and pass away in amazing design. One star has particularly captured the imaginative minds and concerns of cosmologists and the public alike. This star is Balu, a red supergiant of gigantic extent and age, conspicuously situated in the Orion constellation. Its unmistakable reddish color and variable wonder had long been a source of interest. However, recent developments have intensified interest in this brilliant beast. As we explore the possibility of Balu, we find ourselves on the cusp of a potentially incredible event in the life cycle of this star. But what could these movements in Balu mean? Are we witnessing the prelude to a limitless display of inconceivable scale? Balu, generally many times greater than our Sun, is a cosmic behemoth. Its enormous size is almost beyond human comprehension. Imagine a star so large that if it were to replace our Sun, its surface would extend past the orbit of Mars, engulfing Mercury, Venus, Earth, and Mars in its brilliant embrace. This stunning size is not just an exhibition of Balu's physical characteristics, but also represents its stage in the stellar life cycle as a red supergiant. Balu is in the twilight of its existence, a phase marked by expansion and cooling after a life spent fusing hydrogen into helium in its core. Nevertheless, what about the age of Balu? This star, believed to be around 8.8 to 8.5 million years old, is relatively young in human terms yet ancient concerning stellar lifetimes. Its current red supergiant stage is the culmination of millions of years of stellar evolution, a period marked by profound changes and cycles that have transformed it from a hot blue star to the red giant we see today. The life cycle of stars like Balu is a tale of transformation driven by the relentless forces of nuclear fusion and gravity. Balu's distinctive reddish hue is another indication of its current stage. The red color is a result of its relatively cooler surface temperature compared to other stars like our Sun. While the Sun's surface temperature is around 5,500 Kelvin, Balu's cooler surface registers temperatures around 3,500 Kelvin. This cooler temperature allows Balu to emit light at frequencies that give it a red appearance. However, this color is not just a visual trait. It provides insights into the star's condition and the processes occurring within its vast gaseous envelope. Adding to Balu's persona is its historical color change. Ancient Roman and Chinese texts suggest that around 2,000 years ago, Balu was yellow. It was only in the 9th century that Arabic scientists first described it as red. This color shift over human history is not merely a detail in the annals of astronomy but a clue to the star's transformative journey. The variable wonder of Balu is another fascinating aspect. It's a semi-regular variable star, meaning its light sometimes waxes and wanes. This variability is a characteristic dance of luminosity that has intrigued stargazers and sky watchers for a long time. Typically, Balu undergoes a Betelgeuse dimming 400-day cycle alongside a longer cycle that stretches around 6 years. These cycles have been recorded as far back as 1836 by Sir John Herschel and possibly even earlier in local oral traditions. However, what makes Balu truly enigmatic is not just its changing luminosity but its irregularity. Unlike many stars that follow a predictable pattern, Balu occasionally deviates from its rhythmic dimming and brightening, indicating intricate and less understood processes occurring within its colossal structure. Recent groundbreaking discoveries have certainly caught the attention of cosmologists and astronomers worldwide, with a surprising and dramatic change in its appearance, a phenomenon now widely known as the Great Dimming. In late 2019, the red supergiant Balu, one of the most magnificent stars in the night sky and a prominent feature of the Orion constellation, began to mysteriously dim. The star's dimming was so pronounced that it started losing its brightness at an average rate of 0.01 magnitudes per day, reaching its faintest brightness in February 2020. Balu, usually visible to the unaided eye even in light-polluted areas, became unusually faint, a change noticeable even to amateur observers. However, there's one issue with trying to monitor the activities of Balu: the time oddity. When we look at a star like Balu, we are not seeing it as it exists in the present but as it was in the past due to the time it takes for light to travel to us. In Balu's case, at approximately 725 light-years away, the light we see today left the star nearly 7 centuries ago. This delay makes it challenging to predict and monitor sudden changes in a star's behavior, as we are essentially peering into its past. The Balu dimming event served as a reminder of the inherent challenges in astronomical observations and the limitations of our understanding when dealing with the immense scales and time delays they present. The unfolding of Balu's cosmic drama was closely monitored by Andrea Dupree, Associate Director of the Center for Astrophysics at Harvard and Smithsonian, and her team. They used Hubble to examine the giant star as part of a 3-year study to analyze variations in Balu's outer atmosphere. These observations provided a unique insight into the dynamics of a variable star like Balu, which continually expands and contracts, causing changes in brightness. Hubble's sensitivity to ultraviolet light allowed the researchers to probe the layers above the star's surface, which were heated primarily by the star's turbulent convection cells. Further analysis of the Hubble spectra taken at different points throughout 2019 and 2020 revealed the movement of material in Balu's outer atmosphere, particularly the spectra focused on magnesium-2 lines, which are indicative of the star's atmospheric conditions. These observations showed material moving at speeds of around 200,000 miles per hour from the star's surface into its outer atmosphere. This hot, dense material eventually extended millions of miles from Balu and was the precursor to the dust cloud that caused the star's dimming. Dupree and her team estimated that twice the usual amount of material from Balu's southern hemisphere was lost over 3 months during the dimming. This mass loss was significant, especially considering that Balu, like all stars, continually loses mass but at a rate far greater than that of our Sun. The magnitude of this mass ejection and the resulting dimming sparked discussions among cosmologists about whether this event could be a precursor to a supernova. The proximity of a supernova at around 725 light-years from Earth adds to the intrigue, as any such event would be visible from Earth, providing a rare opportunity to witness a cosmic explosion up close. Several theories were proposed to explain this sudden change. One leading theory suggested it was a phase in the supernova process, a hypothesis that gained some traction due to the common belief that Balu is nearing a dramatic end. Another popular theory involved trapped dust, possibly from the star itself, obscuring our view. Balu, like other red supergiants, is known to shed material, and it was thought that this material could form a dust cloud thick enough to dim the star's light from our perspective. A third explanation considered changes in the star's photosphere, the visible surface layer, which could affect its apparent brightness. Further investigation using various observational methods unraveled this mystery. Spectroscopic analyses showed a drop in Balu's effective temperature, suggesting that the dimming could be due to a large dark spot on the star's surface. This theory was supported by the observation that Balu's temperature decreased by about 170 Kelvin during the dimming, indicating significant changes on its surface. Ultimately, the key to understanding this unusual phenomenon came from humanity's sentinel in space, the Hubble Space Telescope. Hubble's observations revealed that Balu's dimming was likely caused by a massive ejection of hot material into space. This material formed a dust cloud that obscured part of the star's surface, significantly reducing the amount of light reaching us from Balu. The dust cloud was believed to have formed from extremely hot plasma ejected from a large convection cell on the star's surface, and then traveled through its hot atmosphere to the cooler outer layers. As it cooled, it formed dust grains, creating a cloud that blocked light from about a quarter of the star's surface. Hubble's ultraviolet light spectroscopic observations, which began in January 2019, were crucial in unraveling the sequence of events leading to Balu's dimming. These observations detected signs of dense, heated material moving through the star's atmosphere in the months preceding the dimming. In December 2019, ground-based telescopes also observed the star dimming in brightness, particularly in its southern hemisphere. This material, initially brighter than the star's usual brightness, eventually led to the formation of a dust cloud as it moved outward and cooled. The hypothesis was that this ejected material and the resulting dust cloud caused the star's sudden dimming. The magnitude of this ejection is truly staggering, putting Balu in a cosmic spotlight. The star ejected an estimated 400 encounters into the inward activities of stars and the powers that shape our divine scene. The story of Balu, a red supergiant on the brink of a possible supernova, highlights the dynamic and unpredictable nature of stellar evolution. Balu's enigmatic behavior. Balu's sudden dimming event in late 2019 and early 2020 puzzled astronomers and sparked intense observation and analysis. The star's brightness fluctuated significantly, raising questions about the underlying mechanisms driving these changes. Theories proposed to explain Balu's variability include the formation of a dust cloud, massive convective cell activity, and changes in the star's photosphere. Dust cloud hypothesis. One prevailing theory is that Balu ejected a large amount of hot material, which then cooled and formed a dust cloud that obscured part of the star's surface. This event, unprecedented in its scale, resulted in a temporary but significant reduction in Balu's brightness. Observations from the Hubble Space Telescope and other ground-based observatories supported this hypothesis, revealing that the star's outer atmosphere expelled material at high velocities, leading to the formation of the obscuring dust. Convection and surface activity. Another explanation involves the star's convective cells, which are massive, hot pockets of gas rising and falling within Balu's outer layers. These cells can cause significant surface activity, including the formation of large star spots or areas of cooler temperature. The variability in Balu's brightness may be linked to these convective processes, which can alter the star's apparent luminosity. Implications for stellar evolution. The behavior of Balu provides valuable insights into the late stages of stellar evolution, particularly for red supergiants. These stars are expected to end their lives in spectacular supernova explosions, but the exact timing and mechanisms leading up to these events remain subjects of active research. Balu's recent activity suggests that such stars may experience more violent and erratic phases than previously thought, shedding large amounts of material in episodic events. The future of Balu. While the exact future of Balu is uncertain, the star's recent behavior hints at a potentially dramatic end. If Balu were to go supernova, it would be a rare and significant event, observable from Earth even across the vast distance of 725 light-years. The explosion would outshine its entire galaxy for a brief period and leave behind a neutron star or black hole, contributing to our understanding of these extreme astrophysical objects. Ongoing observations. Astronomers continue to monitor Balu closely, using a combination of space-based and ground-based telescopes. These observations aim to capture any further changes in the star's brightness and to gather data that could indicate an imminent supernova. The insights gained from studying Balu could refine models of stellar evolution and improve predictions about the life cycle of other massive stars. Broader cosmic context. Balu's story is part of the larger narrative of the universe, where stars are born, live out their lives, and ultimately die, often in spectacular fashion. The study of these processes not only satisfies human curiosity but also advances our knowledge of the cosmos and our place within it. Each discovery, like the enigmatic behavior of Balu, adds another piece to the puzzle, helping us to understand the complex and beautiful tapestry of the universe. As we await further developments, the tale of Balu reminds us of the dynamic and ever-changing nature of the stars, and the boundless mysteries that still await discovery in the vast expanse of space.